The giant piston-engine bombers of World War II were completely obsolete, but the new jet engines designed to replace them kept violently destroying themselves. To transition into the supersonic age, engineers had to solve the deadliest aerodynamic problem in aviation history, the compressor stall. In 1952, engineer Leonard Hobbs was awarded the prestigious Collier Trophy for a mechanical masterpiece that changed aviation forever. By designing the J57 with a dual-spool axial compressor, his team solved the deadly problem of compressor stalls, building the first turbojet to safely crack the 10,000-pound thrust barrier. The J57 was not just an incremental upgrade, it was a desperate fix for a fatal aerodynamic flaw hidden inside earlier turbojets like the J47. Those early engines utilized a single-spool design. Every compressor blade was locked to one single mechanical shaft, forced to rotate at the exact same speed. At high altitudes and full throttle, this worked, but during acceleration from low speeds, the aerodynamics turned chaotic. The rear stages could not push high-pressure air into the combustor fast enough. Because the front stages were locked to that same shaft, they kept ramming massive volumes of air into a severe aerodynamic bottleneck. The air rapidly compressed, violently reversed direction, and blew out the front of the intake. This is a compressor stall. It is not just a loss of power, it is a violent explosion of reversed airflow that can instantly shatter turbine blades and destroy the aircraft. Engineers were trapped. They could not build a larger, more powerful engine without it destroying itself. So, how do you push massive volumes of air through a narrowing mechanical tunnel without allowing the internal pressure to safely vent or adjust? Here's the best part, where we can see the elegant mechanical masterpiece that earned Leonard Hobbs the Collier Trophy. Instead of forcing the air into a single rotating trap, Pratt Whitney split the compressor entirely in half. This is the dual-spool or twin-spool configuration. It features an inner low-pressure compressor at the front and an outer high-pressure compressor right behind it. But crucially, they are mechanically independent. The engine utilizes two concentric driveshafts, a smaller diameter shaft spinning freely inside a larger, hollow outer shaft. The outer shaft connects the high-pressure turbine to the high-pressure compressor, while the inner shaft links the low-pressure sections. Because they are physically decoupled, the two sections naturally seek their own aerodynamic equilibrium. During startup, the high-pressure spool spins aggressively to handle the dense air, while the low-pressure spool rotates at a slower, stable speed, stopping the deadly aerodynamic stall before it can even begin. This physical decoupling provided an unprecedented level of aerodynamic self-regulation. Without needing heavy, complex, variable stator vanes, the J57 automatically balanced its internal pressure ratios. If the airflow changed rapidly, the low-pressure spool would naturally slow down, feeding the high-pressure section the exact volume of air it could safely handle. This mechanical harmony allowed Pratt & Whitney to increase the overall pressure ratio to 12.5 to 1, a staggering efficiency metric for 1952. This engine delivered exceptional fuel economy, lightning-fast throttle response, and a base thrust of 10,000 pounds. It provided the exact, unflinching thermodynamic stability required to power a new generation of intercontinental strategic bombers. By separating the compressor into two independent mechanical systems, engineers created an engine that could automatically shift its internal aerodynamics to match the density of the air, much like a transmission shifting gears to match the speed of a vehicle. But building the ultimate jet engine was only the first battle. To project power across the globe, Boeing had to figure out how to safely mount 8 of these high-pressure beasts onto a single, highly flexible wing. Hanging 8 massive 10,000-pound thrust turbojets off a wing designed to physically flex up to 32 feet in mid-air sounds like a structural nightmare. One severe pocket of turbulence could easily induce enough torsional twist to snap the wing clean off. The Boeing B-52 Stratofortress was not just a larger airplane, it was a radical redesign of aerospace architecture. To utilize the immense power of the Pratt & Whitney J57, engineers had to mount 8 of these engines onto a high aspect ratio wing without compromising the aerodynamics or the structural integrity of the airframe. Burying engines inside the wing, like they did on the B-36, was aerodynamically clean but structurally fatal in the event of an uncontained engine fire. Boeing engineers took the opposite approach. They suspended the 8 J57 engines in dual pods, hanging them far forward of the leading edge on heavy pylons. This was not simply for fire isolation. The swept wings of the B-52 were designed to flex dynamically under heavy fuel loads. By placing thousands of pounds of engine mass forward of the wing's torsional axis, the pods acted as massive anti-flutter counterweights. If the wing tried to twist uncontrollably during high-speed turbulence, the physical mass of the forward-slung engines dampened the vibration. Engineers were literally using gravity and inertia to keep the wing from tearing itself apart at high Mach numbers. Can you imagine engineering a structure where adding heavy weights to the weakest points actually makes the entire system stronger? The J57 did more than just provide raw thrust. Traditional heavy bombers relied on massive mechanical driveshafts connected directly to the engines to power hydraulic pumps and electrical generators. On the B-52, those heavy mechanical linkages were entirely eliminated. Instead, engineers tapped directly into the high-pressure compressor stage of the J57. They bled off air at hundreds of degrees Fahrenheit and routed it through stainless steel pneumatic lines deep into the fuselage. This high-pressure bleed air spun auxiliary air-driven turbines, which then powered the heavy hydraulics and electrical grids. The aircraft essentially used the thermodynamic pressure of its own engines as a central nervous system, shedding thousands of pounds of mechanical dead weight. The final structural victory was chemical. Forcing early turbojets to burn heavily leaded aviation gasoline caused rapid turbine degradation and constant engine failures. The B-52 and its J57 engines were designed from the ground up to burn JP4, a highly refined, wide-cut jet fuel blend. Without the extreme lead bromide buildup scoring the combustion chambers and melting the turbine blades, the mechanical lifespan of the engines skyrocketed. Instead of overhauling an engine after a few dozen hours, the J57 could run cleanly and continuously for hundreds of hours. This thermal and chemical reliability meant the B-52 could loiter near the edge of Soviet airspace for 24 hours at a time, establishing a continuous airborne alert that defined the strategic reality of the Cold War. Switching from aviation gasoline to JP4 was like transitioning a heavy industrial machine from running on crude oil to burning pure, refined alcohol. The thermodynamic efficiency increased, while internal wear practically vanished. The combination of the dual-spool J57 and Boeing's forward-slung pylon design created a bomber with unprecedented range, reliability, and structural integrity. The era of the multi-engine piston behemoth was completely over, replaced by an 8-engine jet that remains in active military service over 70 years later. Let me know in the comments if you think any aircraft will ever match the operational lifespan of the B-52 Stratofortress.